Silicon carbide, specifically the 4H polytype, is the premier substrate for high-voltage power electronics and sensors designed for extreme environments. Its utility stems from a 3.23 electron-volt bandgap, exceptional thermal conductivity, and extreme physical hardness. However, these properties create a bottleneck in microfabrication. Creating high aspect ratio features, such as deep via holes, is difficult because the material resists standard removal techniques. Dry etching methods using fluorine or chlorine plasmas are remarkably slow, removing only 0.2 to 1.3 micrometers of material per minute. Consequently, the industry relies on aggressive mechanical machining and nanosecond laser ablation, driving the material to its physical breaking point. Engineers utilize two different ways to force material removal: applying non-hydrostatic mechanical pressure with a sliding indenter, or delivering high thermal loads via a nanosecond laser. Despite the different physics, kinetic versus optical, both methods stall when attempting to create deep, narrow channels. This suggests the limitation is not merely the bulk hardness of the crystal, but a dynamic defense mechanism triggered by the manufacturing process itself. Under localized stress, the 4H SiC lattice undergoes phase segregation, altering its internal structure in real time. This segregation creates a localized shield. The material present at the start of the cut is physically and optically distinct from the material remaining at the end. The bezel beam is theoretically the optimal optical tool for drilling deep vias because its non-diffracting core provides a massive focal depth. This graph maps the spatial profile of the bezel beam. There is a high-intensity central peak at 0 micrometers, surrounded by undulating side lobes that spread outward. 4H SiC is transparent to the 1064 nanometer near-infrared wavelength used here. The laser's 1.17 electron-volt photon energy is far below the material's 3.23 electron-volt bandgap, which should allow the light to propagate deep into the substrate. These scanning electron microscope images show the result of that propagation. The bezel beam produces shallow, wide craters with significant surface damage. This contrasts with the standard Gaussian beam, which successfully drills a deeper, tighter hole in the same material. This data shows the normalized hole diameter over 10,000 pulses. The bezel beam holes expand rapidly with each pulse, while the Gaussian holes remain stable. Optical theory alone does not account for this disparity. It requires an examination of how the SiC lattice reacts to the specific geometry of the bezel beam. Analyzing the material's response to stress without optical variables reveals the underlying mechanism. Researchers analyzed a scratch groove on 4H SiC generated by approximately 7 gigapascals of sliding contact pressure using micro-Raman spectroscopy. This chart compares the Raman spectra of the damaged regions to a baseline. Curve A represents the clean, unscratched lattice. In the scratched regions, we see distinct broadening and asymmetry in the FTO and LO phonon modes. This spectral shift indicates that the localized pressure is generating internal defects, stacking faults, and residual strain. Under heavy loads, a broad hump emerges between the TO and LO bands, spanning 800 to 950 inverse centimeters. This feature identifies amorphous SiC. Before the material ablates, the crystal lattice collapses into a disordered state. Because of surface polarity, polar SiC crystals cannot easily shed single atomic layers during this amorphization. This flowchart illustrates the resulting phase separation. The metastable amorphous SiC separates into distinct silicon and carbon components. Raman spectroscopy confirms the presence of the silicon component. A sharp silicon band emerges at approximately 500 inverse centimeters. The sharpness of this band indicates the formation of ordered quasi-crystalline silicon nanoparticles, rather than a disordered silicon blur. The carbon component is also visible in the scratch groove. Strong D and G bands appear between 1200 and 1600 inverse centimeters. These bands signal an sp3 to sp2 transition, indicating the amorphous carbon is transforming into graphite. Localized stress forces 4H SiC to segregate into a highly absorptive graphitic barrier. This mechanical phase change explains the limitations of nanosecond laser ablation. The dominant energy transfer mechanism in this context is free carrier absorption. This graph shows how the absorption coefficient increases with temperature. As temperature increases, dopant ionization and valence band activation cause the absorption to scale sharply. When we re-examine the Bessel beam's spatial profile, the impact of the peripheral side lobes becomes clear. These lobes deposit enough thermal energy to trigger the same crystalline to amorphous to graphite transition observed in the mechanical data. The resulting graphitic surface layer has a narrow bandgap and is opaque to the near-infrared laser light. A Bessel beam reconstructs its central core using conical wavefronts that travel from the periphery toward the center. These incoming wavefronts collide with the opaque graphitic layer created by the side lobes. The energy is absorbed at the surface before it can converge into the focal core. The Bessel beam's side lobes build a graphitic shield that stops energy propagation, causing the crater to widen instead of deepening. This unified model explains why the standard Gaussian beam remains effective for deep drilling. A standard Gaussian beam does not possess these wide peripheral side lobes. The thermal energy is strictly confined to the central optical axis. This confinement vaporizes the material directly along the path of the beam before a peripheral graphitic shield can intercept the light. This barrier is a transient, localized material state rather than a static bulk property. Whether applying high-pressure shear stress or nanosecond thermal pulses, 4H SiC defends itself by segregating into the same graphitic shield. This has broader implications for engineers working with wide bandgap semiconductors. Process design and tool selection cannot rely solely on ideal optical theory. Engineers must design for the transient, reactive phases the material assumes under load. Ultimately, success depends on anticipating exactly how these materials chemically and structurally adapt when pushed to their extreme physical limits.